Okay. Fun and interesting heat transfer. Let's talk about. Yeah. Okay, so today we are going to talk about, the how to solve this exact solution. Of course, if you look at this exact solution, you don't want to solve it because it looks too complicated. So what we do is we use a first term approximation, which looks like this. Theta star. So what we want to know is the temperature. To find the temperature of a system, we use this property theta star. By the way, theta star is theta over theta I. Am I recording this one? Which is the temperature of the system minus the temperature of the surrounding fluid divided by the initial temperature minus the temperature of the surrounding, can be determined by this equation, theta star 0 cosine zeta1 x star. And this theta star can be determined by C1 E2 minus zeta1 square Fourier number. And this equation explains when you have a solid such as this plane wall, let's assume that initially the temperature of this plane wall was 20 degrees Celsius and the surrounding fluid is going to be at high temperature. Let's say T infinite is maybe 200 degrees Celsius. Then you want to know how long it's going to take to raise the temperature of this plane wall. And we assume that this is not a lumped system. By the way, lumped system means that the temperature inside the solid is going to be uniform, such as when the surface is near 200, let's say, the 190, then the center of the solid is going to be maybe 180, so that we can have a almost uniform temperature distribution within the solid. Then it is lumped system. On the other hand, this one is not. In that case, the temperature distribution within the solid is going to look like this. So due to the heat transfer from the fluid to the surface of this solid, the surface temperature is going to increase first. So near the surface, we can say maybe 190 or something, while the temperature of the center of the solid is going to be still near the initial temperature, let's say 20 degrees Celsius. So there's a significant temperature gradient in the solid. In that case, we cannot use lumped method. We have to use approximate method. The solution to the approximate method is written here. But when you want to study how this temperature of the solid changes, we don't actually, we are not actually interested in the temperature near the surface. When we design an engineering system, our focus is going to be the critical point when the temperature is the lowest or the temperature is the highest. So in this problem, the location, where we are interested in is going to be the center line, right? So if you, let's say that you want to raise the temperature of this solid at least 100 degrees Celsius, you want to see, the temperature near the surface? No, you want to see the temperature at the center. So when the center temperature reaches 100 degrees Celsius, you can say anywhere in the solid is 100 degrees Celsius or above, right? So the critical point in this system in terms of heat transfer is going to be the center. Then in this equation, which, the part of this equation shows the temperature of the center. That is the one written in red. So theta star 0 means, according to this equation, theta 0 minus, T0 minus T infinite over Ti minus T infinite is T1 E2 minus Z1 square Fourier number. In this case, T0 is the temperature at the center line. While the T infinite is the temperature of the fluid and Ti is the initial temperature. So when we do a heat transfer analysis, most of the times we want to see the temperature at the critical point, which is the center of the solid, that is T0. So if you only want to determine T0, then you don't have to solve the entire equation. You can just solve this equation. That will give you the temperature at the center line, which is this one. Okay? Then, how can we solve this equation? Let's look at the right-hand side. We have two coefficients. One is C1, the other one is Z1. So these two can be found from a table. And Fourier number is thermal diffusivity alpha, which is a material property, times time t over characteristic length square. So if you know this equation, then you can determine the relation between the temperature of the center and time t, which looks exactly the same as the lumped method. Just for your information, the lumped method equation is theta star, which is T minus T infinite over Ti minus T infinite is E2 minus HA over rho VCT. So in this equation, what we want to know using this equation is the relation between the temperature of the solid and time t, these two. And in this equation, that's the same. Instead of t, we are going to focus on the center line, T0, and time t. So you can see, we can find the relation between temperature at the center line and time t, which looks similar to this equation. Then why this one is just t and this one is T0? Because lumped system, we assume that the temperature of the solid is uniform. So anywhere in the solid will have the same constant T. On the other hand, when we have an approximate solution, we have a significant temperature gradient in the solid. So we are going to focus on one critical point, which is the center line. So we can find an equation that shows the relation between the temperature at the center line and time t. Okay? So whenever you have a transient heat conduction problem, the main key question is going to be, what is going to be the temperature of the system at time t? Because temperature is a function of time. So if it is lumped system, you use this equation to determine the temperature of the solid at time t. When you have a, when you don't have a lumped system, since there is a significant temperature gradient, we are going to focus on the critical point, which is the center line, and the temperature, the temperature at the center line can be determined by using this equation as a function of time t. So they are the same thing. Okay? Then we are going to study how to use this equation. That means we need to know what table do we use to evaluate C1 and Z1. We can use table 5.1, which is shown right here. There are three simple geometries that we are going to use. The first one is plane wall. In this case, we are going to focus on plane wall, looks like this. And we want to know the temperature at the center line of this plane wall. So this is T0, and the characteristic length L0 is going to be half of the thickness. Then the governing equation is theta star, which is theta star 0, which is theta divided by theta 0, which is E minus T0, I'm sorry, theta 0 divided by theta I, T0 minus T infinite over Ti minus T infinite is going to be E2, I'm sorry, C1 e to the power Z1 square times Fourier number. By the way, this Fourier number is alpha t over characteristic length square. When we have a plane wall like that, you can go to table 5.1, and the first column is Biot number. By the way, in this case, Biot number can be determined by H times characteristic length L of L divided by thermal conductivity K. And this L is going to be half of the thickness of this plane wall. And when this value is greater than 0.1, then we cannot use the lumped method. We use this approximate solution, and using this Biot number to determine Z1 and C1 from this table 5.1. That will give you C1 and Z1, and alpha is a thermal property that you can find from a table, and you just need to know the characteristic length L of 0 to determine the center temperature. And there is another geometry. The first one is, by the way, this one is plane wall, and the second one is infinite cylinder. And this one looks similar. And in this case, we want to determine the temperature at the center again. And the radius is going to be R0. And we use this R0 to determine Bion number. Bion number is H times R0 divided by thermal conductivity K. And using this Bion number to determine C1 and Z1 from the table 5.1 and use this governing equation, which is theta star 0 is theta 0 divided by theta I, which is the temperature at the center minus the temperature of the fluid divided by the initial temperature of the solid minus the surrounding fluid temperature is C1E2 minus Z1 square Fourier number. In this case, Fourier number is again alpha times T over characteristic length square. And there's one more geometry, which is sphere. In that case, the radius is going to be R0, and the rest of them is the same. Once you determine R0, you can find Bion number. And once you get Bion number, find C1 and Z1 from the same table 5.1, and use this equation. So there are three geometries. One is plane wall and infinite cylinder and sphere. So depending on your system, you can select one or a combination of them to determine the temperature at the center point or center line. That's how you determine, that's how you solve heat transfer problem by transient conduction. Sometimes, you want to know, other than this temperature of the center, such as, yes. Oh, my mistake. Yeah, you're right. So there's a negative in front. And if you want to know how much heat transfer is required, to change the temperature of the center line from the initial temperature to the final temperature, this is the equation. Q over Q0, by the way, Q0 is this one, can be determined by, can I see this one? Cause of the background, 1 minus sine Z1 over Z1 I 0 star. So that's how you can determine the amount of heat transfer. So that's everything about, the three geometries: plane wall, infinite cylinder, and sphere. Now we have one more geometry, which is semi-infinite solid. Oops. Semi-infinite solid. This semi-infinite solid is different from the other three that we studied. So plane wall, we have two boundary conditions. One is at the center. So one boundary condition is going to be the temperature profile is going to look like that. So we can say the slope is going to be 0 at the center. That is boundary condition number 1. And we know the temperature at the surface. That is boundary condition number 2. So this is plane wall. So we have two boundary conditions. And when we have an infinite cylinder, we also have two boundary conditions. One is at the surface, boundary condition number 1, and boundary condition number 2 at the center. And if we have an infinite sphere, we also have two boundary conditions. Boundary condition at the surface, and another boundary condition at the center. So by using these two boundary conditions, we can solve the second order differential equation on the left hand side of this governing equation. But if you have a semi-infinite solid, let's say this is a solid, and we don't know how deep it's going to be. And initially, Ti is 20 degrees Celsius. And suddenly, this surface is exposed to a fluid whose temperature is 100 degrees Celsius. Then what's going to happen? We will know that the temperature of the surface is going to increase first. So up to this much. And the temperature is going to decrease from the surface, and eventually it's going to be near 20 degrees Celsius, like that. So this is the temperature distribution for a semi-infinite solid. Then how many boundary conditions do we have? One boundary condition at the center, but that's it. So because we don't know how deep it's going to be, we cannot use a boundary condition on the other side. So to solve the heat transfer for a semi-infinite solid, we need to make some assumptions. First one is, what if we have a constant surface temperature? So the first assumption, case 1, is going to be temperature of the surface is constant. And the second assumption is going to be uniform surface heat flux. So case number 2, the heat flux at the surface is constant. Or case number 3, the surface is not at constant pressure or constant surface heat flux. So we assume that it's going to be convection takes place at the surface. Case number 3. That's a convection heat transfer. Q by convection, that is what happens at the surface. So depending on each case, we have solutions available. So case number 1, this is how we determine the temperature of the solid with position x and time t. If we assume that it is uniform surface heat flux, this is how we determine the temperature at a certain position x and time t. If it is convection heat transfer boundary condition, And this is the temperature of the surface at a position x and time t. So position x means the depth from the surface. So depending on which case it is, you can solve this solution to determine the temperature of the solid at a certain location and time t. One thing you need to make sure you understand is this ERF. This is called error function. How can we solve this error function? It's actually very simple. You can go to error function table. And there's a table, something like this. See, can I see it? No, it is not. I need to pay, right? Go away. Let's find another error function table. It looks like something simple. This one. Oh, this one looks good. So this is, download it. Okay. This one is the error function. That is not an error function. That is error function C. That means complementary error function. We're going to talk about that later. Where is error function? This one. Oh, here is the error function. I can see that. Let me find error function table. Looks simpler than this one. That's a complementary error function. Maybe Wikipedia. Error function. Oh, do I have to pay? Where is the error function table? No, there is error function table. Let me find one. Oh, maybe. It's a complementary error function. Montana State University. No, that's not Michigan. That is out of nowhere, isn't it? Nobody from Montana, right? Okay. I've never been there. Is there any big city in Montana? Montana. Where is this error function table? I want to find it. Oh, right here. Okay, that doesn't look pretty. Oh, right here. So this is the error function table. So I will provide this error function table if there is a semi-infinite, the solid problem. But you need to know how to use this table, which is actually very easy. So this x is the input for this error function, and this error function x is the output. So if you go back, how can I go back? If you go back here, it says error function of x over 2 times square root of alpha t. If you determine that whatever inside is approximately 0.5, then you need to find error function of 0.5. So to determine that, you can go to error function table. So the x is 0.5. Where is 0.5? Oh, right here. X is 0.5. What is the output of the error function? 0.19146. Then you go back and say this one is 0.19, I forgot that, 146. That's how you solve error function. You don't have to actually solve, you use a table to determine the value for this error function. Or sometimes you have to do backward. Let's say, I know the temperature, the ratio of this one, and it is approximately 0.4. Then how do we determine error function, whatever the input of this error function? Then you go to error function table. So the output is 0.4. What is the input? Then you go back to the error function table, find 0.4, which is between these two. Then you can find x by linear interpolation is going to be approximately 1.28 or something. Let's say 1.28. Then you go back and say whatever inside is going to be 1.28. Then this 1.28 is what? X over 2 times square root of alpha t. So if you know x, you can determine t. If you know t, you can determine x. Okay? Yes. Okay. So in the table, x is the input. And in this, the solution, the input is x over 2 times square root of alpha t. So the x here and the x in the table, they are the same. That is the distance from the surface. Okay. So what we want to do is that we want to calculate the temperature of a semi-infinite solid. Can be at the surface, or can be away from the surface. And how away? Maybe 1 meter. Then x is going to be 1 meter. Okay. So there are 3 cases. Case number 1, constant surface temperature. Case number 2, uniform surface heat flux. Case number 3, convection heat transfer. For all of them, you have a temperature. The solution is available, which is which contains error function. So if you have an error function table, you can solve that equation. There's one more thing. If you look at this equation, let's say case number 2. At the last term of this temperature equation, it has error function C. This is not an error function. ERFC means complementary error function. The complementary error function is nothing new. This is just 1 minus error function. Okay? So you can go to complementary error function table, or you can use error function table and use this equation to determine the output of complementary error function. We have a practice problem at the end, so we are going to solve the problem together, so you can get to know how to use these equations. Okay. So in a summary, we studied how to determine the temperature of the center line in a plane wall, in an infinite cylinder, and sphere. The governing equation for these 3 are theta 0 star is theta divided by theta star, which is theta 0 over theta I, T0 minus T infinite over Ti minus T infinite. So theta star is kind of the temperature scale, non-dimensionalized. temperature. The temperature of our interest minus the temperature of the surrounding divided by the initial temperature of the solid minus the surrounding temperature. That can be determined by C1 E2 minus Z1 square Fourier number. So we can use this equation for different coefficients from a table, so you can determine the temperature at the center, which is T0, as a function of time t, alpha t over characteristic length square. Or we can have a semi-infinite solid and the temperature distribution in this semi-infinite solid can be determined by three different cases. So there are three solutions available. Case 1, case 2, and case 3. Just for your information, when you have case 1, the temperature distribution is going to be T minus Ts over Ti minus Ts. By the way, Ts is the surface temperature. Is going to be at a function of x divided by 2 times alpha t. So using these equations, you can determine the temperature at the center line or the time t if you know the temperature at the center. The last part of this chapter 5 is called multi-dimensional effect. What does it mean? By using this equation, you can determine how the temperature change at the center line of plane wall, infinite cylinder, and sphere. However, not every engineering system looks like plane wall, infinite cylinder, or sphere. So what about if you want to study, let's say, this cell phone? Then this cell phone looks like a cube. So this is the cell phone. And let's assume that you're working for the thermal management department of the cell phone company. It's a Google. So you're working for, the Google phone division, and you're working for the heat transfer analysis. So how can you determine, what is going to be the temperature of this cell phone after, the watching, the YouTube for 5 hours? Okay, then can you determine that? Yes, because you will know how much heat does it generate, and you will know, how long it's going to take. Then you just need to use this equation. By the way, we assume that the cell phone, the Bion number, is greater than 0.1. So we want to determine, what is going to be the temperature of this cell phone after watching, the YouTube for 5 hours. How long it's been? 5 hours. And we want to make sure the temperature is not that hot, so you can hold it. Or the temperature is not that hot, so you can, maintain the battery, the performance as usual. Because when temperature goes up, the battery, the performance goes down. If you have a toy in Michigan, if you have a toy in Texas, the one in Texas, the last shorter than the one in Michigan, right? Not necessarily, because the indoor temperature is about the same. But what about the toys outside? Under the sun, the batteries, the performance goes down, so the battery cannot last. as long as the one in, the Michigan, right? No? Anybody from, the electric engineering department? No one? Oh, I didn't know that. But usually when temperature goes up, the performance goes down. That's in general. So there's a threshold temperature range when you have the optimized battery performance. Okay, so you want to make sure that if this one doesn't go, the broken after, the watching YouTube for 5 hours. Let's assume that the maximum temperature this battery can withstand is going to be the maximum temperature. T max should be less than 50 degrees Celsius. Then what you want to calculate is going to be what is going to be the temperature of this cell phone after 5 hours. Then how can you solve it? Which one can we use? Can we consider this cell phone as a plain wall or infinite cylinder? Of course not. Sphere? No. Then what is going to be? Can we assume that this one is a plain wall? Not necessarily. What is the heat transfer direction for this plain wall? The heat transfer direction for this plain wall is going to be, from the side this way. Q, or the other way. Q. So the temperature heat transfer from the cell phone to the surrounding is going to be to the side. But what happens in the cell phone is going to be there is a heat transfer to this direction Q. There's a this direction, the Q, but there is also heat transfer in this direction Q and this direction Q, and there is a heat transfer. I need blue. Where are you? Oh, here. This direction and this direction. So considering, the heat removing point of view, which one is more efficient between plain wall or the cell phone? This one is more efficient because you have more, the heat transfers. Then, can you determine the final temperature of the cell phone by you assuming plain wall? Not necessarily. So what can you do? You can combine plain walls. So one plain wall is going to be this way. Or let's say this way. So there's a one plain wall and another plain wall this way. And one more plain wall this way. So we can combine 3 plain wall because one plain wall is one-dimensional heat transfer. If you combine 3, then you can study 3-dimensional heat transfer, right? So in this case, you can calculate theta 0 star in this direction, and you can calculate theta 0 star in this direction, and you can calculate theta 0 star in this direction. By how? By using the equation that we know. By the way, this can be C1 E2 minus Z1 square Fourier number. What about this red up and down C1 E2 minus Z1 square Fourier number? What about this blue, these two directions? C1 E2 minus Z1 square Fourier number. Now you can calculate, you can multiply all these 3. Theta green multiplied by theta red multiplied by theta blue is going to be theta 0 star. This is not for plain wall, but for this cube. That is for cube. So if you calculate these 3, and let's say that you got maybe 0.5, then let's assume that the initial temperature when we didn't, by the time when we start watching YouTube, initial temperature is 20 degrees Celsius. the surrounding temperature T infinite is so there's a heat generation. So initial temperature is 20 degrees Celsius. The surrounding fluid temperature is going to be, let's say, 60 degrees Celsius. And we want to know what will be the temperature at the center. Then TO minus T infinite divided by TI minus T infinite is going to be 0.5. Here you have a 60 degrees Celsius, 20 degrees Celsius, 60 degrees Celsius. What is the temperature of the center? 40 degrees Celsius. So you can determine what is going to be at the center of this cell phone after 5 hours of watching, and then you can determine, oh, 40 degrees Celsius less than 50, so you can use that. This is called multi-dimensional effects. So you're combining, the more than one approximate method to make your own geometry. What about if you want to, I don't know why this one is here, but what about if you want to, the design an electrical system, electronic system looks like this short cylinder. Then can we study this thermodynamically, assuming that this is a transient conduction? Yes. Hey, how? This can be considered as a short cylinder. So we can have, we have a short cylinder like this. Then this is going to be a combination of infinite cylinder and plane wall. So we can study theta star 0 for this plane wall and theta star 0 that is for infinite cylinder. So this one is plane wall. And we can use the same equation, C1 E2 minus Z1 square Fourier number, C1 E2 minus Z1 square Fourier number. If you multiply these two, then you get theta 0 star. This is for a short cylinder, which can be, determined by multiplying these two. Then the temperature at the center of this short cylinder is going to be T0, this one, minus T infinite divided by Ti minus T infinite. So you can determine the temperature at the center. That is called multi-dimensional effect. Okay? Any question? That's everything about chapter 5. So that's everything about chapter 5. Let's solve two problems together. Yes.
Equation like this, but for spheres.
What?
For a sphere. We didn't use the equation.
Your equation looks the same. Yeah. We use just different coefficient. Where is the coefficient? So here, the first two columns are for plane wall. Another two infinite cylinder. The last two is going to be sphere. Okay. So based on that, let's solve a problem together. The first problem. Is there more problems? Yeah, there's more problems. Oh, I don't like that. Oh, there's more. 3 problems. No. The exam is going to be Tuesday in the week of Thanksgiving. A week from today, right? Tuesday. A week from today. A week from today. Yeah. We had a discussion about that, right? That's what the majority of you agreed, wanted to have the exam on the week of Thanksgiving, right? Okay, so we have a steel plate whose thickness is 0.1 meter. We have the density, specific heat, and thermal conductivity. Why do we need them? In transient heat conduction, we need to know thermal diffusivity alpha. By the way, it can be calculated by K over rho C. And we have everything, so you can calculate that. Is that right? I don't know. You can calculate that. Meter square per second. I can give you the unit. All right. And initially, Ti, the initial temperature is 200 degrees Celsius. And we want to make sure that everywhere in the steel is going to be at least 550 degrees Celsius. So where should we look at? Somewhere near the surface? No, the center should be at least 550 because this is the lowest temperature in the solid. So we assume that the temperature of the center should be 550 degrees Celsius. And what about the surrounding fluid temperature? 800. T infinite is 800 degrees Celsius. We have a convection heat transfer coefficient H, which is 250 watt per meter square Kelvin. And how long should the plate be left in the furnace? So it's a transient conduction problem because the temperature of the system changes from 200 up to 550 degrees Celsius. So it's a transient conduction problem. That's what you need to determine first. And there are two solutions available in transient heat conduction. The first one is lumped system. And the other one, second, is approximate solution. By the way, lumped solution is theta star, which is T minus T infinite over T, I minus T infinite is E2 minus HA over rho VCT. We all know that because we studied that last week. What about approximate solution? Approximate solution is theta star, not theta star. It's going to be theta 0 star because we need to show that we are only looking at the center. So the center is going to be T0. That is T0 minus T infinite divided by Ti minus T infinite is C1 times E2 minus Z1 square Fourier number. So to determine whether it is lumped system or not, we need to calculate what? Biot number. How do we calculate Biot number? Biot number can be determined by H times characteristic length over thermal conductivity. This characteristic length can be determined by volume divided by surface area. However, in this plane wall, we do not know how to determine volume and the surface area. So in that case, we use half of the thickness, L0, which is 0.05 meter. So we are going to use this one. So characteristic length should be 0.05 meter. By the way, if you are able to determine volume over surface area, that's how you are going to determine the characteristic length. That L or L0 can be only used when you have a plane wall or infinite cylinder or sphere. Okay, not sphere, plane wall or infinite cylinder. Or you cannot determine the volume and characteristic length because we do not know the length of this plane wall, right? And H value is 250. Thermal conductivity is 48. So if you do the calculation, you get beyond number 0.26, which is greater than 0.1. When you see this number, you may not be happy because we cannot use lumped system. Because to use the lumped system, beyond number should be less than 0.1, right? So we have to use approximate solution. Beyond number is 0.26. Then we go to the table. Table and look for beyond number 0.26. Beyond number 0.26 is, unfortunately, greater than 0.25, less than 0.3. So to determine 0,1, you need to do a linear interpolation. To determine C1, you need to do a linear interpolation again, so twice. I will do my best to minimize the linear interpolation in your exam. So you may get beyond number, exact number on the table. Okay? I will do my best. There is no guarantee in lives, right? I will do my best. Because I may make a mistake. I don't know. But I will do my best to minimize the number of linear interpolation. Anyway, if you do, we get C1. I have the number. C1 is 1.0396. We have a 0,1, 0.488. What about Fourier number? Fourier number is alpha times T over characteristic length square. And what is the characteristic length? Uh, 0.05. Alpha can be found from here. Oh, my bad. Good. Okay. Then here, T0 should be 550, the surrounding fluid 800, initial temperature 200, surrounding 800. So we have everything but time T. Can you determine time T? Yes, 861 seconds. Okay, yes. Can you calculate V? That's why. If you can calculate V over area, then you can use that characteristic length. If you cannot, when you have a plane wall or infinite cylinder, in the case, you can use the half of the thickness or the radius. Other than that, use the exact volume over area. Yes. So it burns, so when you cook meat, sometimes your surface get burned. Why is that? The heat transfer from the pan to the surface is very high. But heat transfer from the surface to the center of meat is very low because meat is not a lumped system. Pan is. That's why there is a, the meat is a kind of bottleneck. So the heat cannot, go through. So heat stays there. What happened? It burns the surface. So if you want to be a good chef, you need to know, the heat transfer. No. Okay, the next problem, as part of a heat treatment process, we have a cylindrical 3 or 4 stainless steel rods of 100 millimeter diameter are cooled from the initial temperature. Okay, so now we have an infinite cylinder. What time is it? Oh, we have 7 minutes. Yeah, that's a lot of time, right? So the initial temperature Ti is 500 degrees Celsius, and the surrounding fluid is at 30 degrees Celsius, and we have H value 500, and we want to make sure the center of the rod drop down to the 50. So the center temperature should be 50 degrees Celsius. How long does it take? And there is a second problem. What is the nominal rate at which the energy must be extracted from the bath? Oh, forget about that. We're not going to study that. So let's solve this problem. We first, every time when you see a transient heat conduction problem, you need to show this is the Bion number. Don't jump, jump into, the solution, like, let's say I'm going to assume this is a approximate solution. No, you cannot do that. You need to show this is the Bion number. Because of that, I'm going to use the lumped solution or approximate solution. So you need to justify, the why you're using that solution. So Bion number first. So to determine this Bion number can be found by radius h of h times radius over thermal conductivity. What is h? Oh, where's my red? Oh, right here. What is h? 500. What is r? 0.05. What is thermal conductivity? Oh, it's not given. Let me give you the thermal conductivity. It's 19 watt per meter Kelvin. So if you do the calculation, this Bion number is greater than 0.1. So not lumped. So lumped? Unfortunately, no. So what is our solution? Theta 0 star, which is T0 minus T infinite over Ti minus T infinite, can be determined by C1 E2 minus Z1 square Fourier number. Fourier number is alpha T over characteristic length square. So from this equation, we can get C1 and Z1 from this Bion number. By the way, Bion number is 1.316, and the coefficients that you can find from table 5.1 is 1.2486, 1.3643. Radius is 0.05. Alpha is, where's alpha? Oh, let me give you the alpha, 4.4 times 10 to minus 6 meters square per second. By the way, this alpha is a material property. You can find it from a property table at the end of your textbook. I'm just providing it to save your time. Initial temperature 500, surrounding 30. The center 50, surrounding 30. So we have everything. Can you determine time t? Yes, we can. Time t is going to be 1031 seconds. So that's how much time you need to put this rod in the what? In the oil, which is maintained at 30 degrees Celsius. That's the nominal rate, which is not that important because it's a transient heat conduction problem. The rate of heat transfer changes. Very significant, goes down depending on the temperature decay. So it is changing. So the nominal rate, I don't think that is important. Of course, you can calculate the total heat transfer rate. You can do that by using this equation as I show you. If you know, if you already calculated theta star and zeta 1, you found it. So you can use this equation to determine the total heat transfer rate. Can be important, but not the nominal rate. I think, you know, that we can skip it because there are just too many materials that we need to cover. Okay. So in the exam, we are going to focus on the temperature and time, you know, the relation. So don't worry about, you know, the nominal rate of heat transfer, which I assume not important. We have one more problem. Really? That is about semi-infinite solid, which is very simple. So it's going to take about 2 minutes, but we don't have 2 minutes, so we will do it on Thursday, but still we are going to have our second exam on Tuesday. Okay? Yeah, we can do that. We will do a quick review on Thursday. Today, Thursday, right? Okay. So this Thursday, we are going to do a review, and maybe we need to check the attendance, right? So let's do that this Thursday. All right, see you later.